Hi, welcome to Introduction to C. My name is Nate Nessler, and this is for Hyperactive Studios. Now, we're going to go over how to code in C. And right now we're in Ubuntu. You can download NetBeans IDE 7.3, like I have done, and you can install it. This will work on Windows, work on Linux, will work on Mac OS X. I'm using Linux here, but you can use one of those other operating systems. This is my preferred operating system, so I'm going to be using that for this demonstration. In addition, though, here we can do a lot of different things here with C. I'm just going to break down a very basic program at first, and then we'll add some more stuff to it as we go along. You can actually do more than just Java in NetBeans. You can also do C and C++ and several other languages. So let's have a look at that real quick. So if I go to File here, and I say I want to do a new project, it comes up with a whole bunch of different options that I have here. Now, I have it set to C and C++ right now. But in this case, I don't have an existing source code here. I'm going to be writing it from scratch. So for that reason, I'm going to choose C and C++ application. Now, if I was doing a graphical program, here I want to do the C Qt application. So I could do a graphical one, and that would run on both Windows, Linux, Mac OS X, etc. Qt is a wonderful graphical library if you want to do graphical programming with C or C++. I highly recommend it. It is really quite nice and is cross-platform compatible. All right. But with that said, I'm going to simply say next here, and it's going to give me this little pop-up here, and things I can choose. In this case, since we're doing C, I'm not going to choose C++, although C++ is probably the most common programming language to code in out of the stuff. We're actually going to do one in C. I do have videos on C++ though, but they're more advanced if you want to check those out. Alright, so here we have, and let's just do program called find voltage, like that. What we're going to do is we're going to find the voltage. It's a very simple algorithm, and we can make it fairly easily here for this. We'll just leave the project makefile as makefile. That's standard. Don't really want to change that. Leave that alone. Your main file should probably be called main, to be honest with you. And build host would be localhost. That's going to stay that. That means yourself. That points to yourself. So most of the time you want it to be yourself and not build it elsewhere. But you can do that. In the collection tool, in this case we're going to use the GCC Juno compiler here. That's what's going on with this right here. So we're going to leave it with that one. That's a good compiler. It works great. Love that compiler, especially for C. Whole Linux is written on it. And let's say finish. So once I do, it's going to build up my project, and pow. I should have something now. Alright. So where libraries are, and then this is where my main code file is here. And double click on that, and it comes right up. Alright. So automatically included a couple things for me, standard lib and studio IO. Actually, on this one, really don't need standard lib, but it's whatever. Let's go ahead and bring that down because I like it like that. Return exit success would be the same thing as return 0. It's just this is a static, basically a constant that shows that this is working correctly. So that's how you do that. Very cool. But you notice it starts typing up everything for you, like so. I guess let's put my name in here. Why not, right? Alright, so there we go. And it's just stored in a comment. It has a nice little starting professional comments there. We could write up some more comments about what our program does, which would be a good idea as far as that goes. Anything in these slash and a star here is a comment. What this means is that the computer ignores it. So the computer is going to ignore anything starting at the slash star here and ending with the star slash. So all this stuff, the computer completely ignores it. This is great because you can leave messages to yourself and the computer will ignore it. It doesn't slow down the program at all because since the computer ignores it, it doesn't even get included when the code gets compiled down and turned into an executable binary, an actual program that runs. So for that reason, this will save you a lot of headaches by commenting stuff correctly. On another note, you can eliminate you can also comment a single line. So this is really useful because you can also comment out a line of code. So if I don't want to make use of that line of code, but I don't want to delete it, maybe I want to bring it back later, I can simply just put // in front of it and comment it out. This keeps you from having to do both /* and then / to comment out a single line. It's just a lot faster. Maybe I want to do a single one like here. This returns correctly, meaning the program. No errors. No errors. There we go. Something like that. So I could add a single line comment like that too. So that's what it's really meant for, but you could also use it to comment on lines of code, and that does simplify and make things better. So very, very cool and very, very useful. Okay, so this lets us include libraries of code. What this means is that instead of writing all the different functions for every single thing we want to do that you could think of, there's already a bunch of them been written by other programmers a long time ago, and it'll make your life so much easier. So instead of writing everything known demand, you just include their libraries of code, and you could go in and read these .h files and read all the different functions in them. I kind of know them off the top of my head, and so we're just going to use them in here, and so you'll learn them too. But there's a bunch of different functions in here that are possible to make your life a lot easier, so that way you don't write as much code. And the way to access that is simply say #include. Now, the reason I don't have to say where it is on the computer is these are so standard that they come with C compilers. So every C compiler comes with these standard set of libraries, and you just simply say the library you want, and it's libraries end in .h, so that's their file extension, and so that gets included. And since it's the standard ones, you notice you have these these open greater than, less than signs. This is required for standard ones. If you're making a custom one, I think you use double quotes if I remember right when you include it, and you need to put it in a location to find it, preferably in your project. But anyhow, here are those files, and there you go. Down here in the main, we have int is our return type. Int means like a whole number, integer, and it's going to be your return type on this. This means that it's going to return a whole number from main, and that has to do with this return here. Now, if it returns a 0, it was successful. It ran correctly. If it returns 1, 2, 3, 4, etc. Those are different error messages. So your program really just, for the most part, you want to return 0. But if you do encounter an error, you can throw different types of errors to the operating system, and then it can get stored in its logging features, and it would actually appear in the system logs of the computer operating system. In case in Linux, it would be in your log files inside of var. So var/log, etc. in there. So that's where those would appear. And so people can use it to help troubleshoot the program, find out what they did wrong or whatever when they're running your program. It may not be an error with your program. It might be something they're doing, or something they're passing to it or whatever, and then they can find the mistakes of what's going on and correct it. And like I said, it's not with your program, it's with their setup or what they're doing. Int here, argc, char ** argv. Okay, what is this? Well, this means we have a certain number. This is our argument list here for how many arguments were passed in when they typed in our program. So we have our program, it'll be named something like find voltage, right? And then they will pass in a number of arguments. This is the number of arguments that are getting passed in. And then this is the entire list of arguments here. This has to do with char **, and this has to do with pointers. I'm not getting into it. It's too advanced for first introductionary explanation of C. So for that reason, I'm not going to dive into argv here with char **. But just realize that is a double pointer, and we're not going to get into it right now. And that's because we're doing a pointer list. It's very efficient, actually, to do it that way, but I'm not going to get into it right now. But it does make it really fast. Essentially, okay, I'll explain this real quick, not in depth, just very basic. The pointers, they basically mean a way of accessing the exact memory addresses of the different items in RAM. because all your variables get stored in RAM. So this is a way of actually accessing those variables as they sit in RAM. And so for that reason, you're able to then access that variable directly. And I'll leave it at that. All right. So, yeah, that's enough for that. Okay, so just a real quick one, just to kind of go over some stuff here fast. Over. Okay, so if I want to do a bunch of constants and things like that, I could do that up here above my main, actually, if I wanted to. Let's do it up here and say define. If I say define like this is how I'm going to create a constant. And I could say something like pi in here, and then I could say something like 3.14, etc., 56, I think it is. Something of that nature. This will define a particular number. And it's going to get assigned to pi variable. Now, I make it all caps by convention. That's what we always do here. It's a standard programming convention in every programming language. Please follow this convention. You will be non-standard with the entire industry otherwise if you don't. So don't do that. You will stand out like crazy in a bad way. So you definitely want to make this all caps. The reason why we do this is if I'm using this in some kind of calculation down here, I can just type in pi. And I can multiply, like my radius. Maybe my radius is 5 or something like that. By it, and then maybe it equals radius. Maybe my radius is a double, which I'll get into that in just a second. So there we go. That's all correct lines of code there. So my calculation. If I need to add extra precision or something like that, I can come in here and just add it. And then if I have like tons of different code, maybe I have like 10,000 lines of code or something like that, right? And I have to access this pi several times. The wonderful thing about this, not only am I just reading this as, pi times radius, it's probably be squared, so it'd be like 5 squared like this. So this is much better than these individual numbers like this. Individual numbers, you have to come in and change them everywhere where there is a mistake or error. Of course, it wouldn't be radius, it would be, and 5 would be the radius, and then you would have pi to get the circumference area of the circle. But anyways, whatever. You get the idea. But it's much better in these single numbers, because if I'm coding this, I don't know what 5 means when I go back to read this code later on, and I probably won't remember. But I can have one quick look at pi and know what it does. This is also great when you're working with other people on a team, when you're programming, and that you can actually have something be, it's called verbose, where it's like well written, to where you can just kind of understand what it means. So that gives you some idea of how that works. Okay. So, and if I need to update everything, see, everywhere pi is being used, it's real simple. I just come here, add the value, change it, whatever, and everywhere pi is supposed to be used, it gets changed. The thing about writing these single individual numbers, you might accidentally go in and change a number that wasn't supposed to be changed, and now the program doesn't work. You have to go through and figure out. The program will still run and compile, no problem, but it's going to be a logic error, and you'll have to hunt through the program and try to find the logic issue. It can take quite a while to find those. So, it might not be straightforward. So again, do things in a clean, professional way. And the reason why we do it that way is because it saves time, effort, headaches, etc. And we just use this define like this to do that. And then, when you change that everywhere where it's supposed to be pi, it gets changed and it just works. This is also pre-processed, which means this gets compiled and executed prior to the rest of the code. And since it's a constant, it means that it can't change. So I can't assign a value to pi later on because it is a constant. So that's never going to change, and I can't change it once it's set in stone. Essentially, it's set in stone. And it also makes it run faster too. So anything that's pre-processed like this was going to run quicker. All right. So that's how pi as a constant works. And here's how we do our radius, our variable in this case. Now we're going to be finding voltage, so this isn't going to make any sense for what we're doing right here. But I just want to show you how to define and create a constant real quick there. So again, it's completely pointless for this particular program, but I did want to show how to do this. Alright, so I'm going to say v, or I can make that lowercase v. It's fine. And then I need another double. So double just means a decimal number, so like 0. Da 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 da. But it's got a massive range, massive range. It's got twice the number of bits that a float has. So I could also use a float here, but that's not as big as a double. A double is going to be a much bigger number. So I'm just using double right now to define this. So if I want to do the electrical equation for voltage, then I need to have I, R, and V defined. So I need I here, and I'll make that equal to 0. What I'm doing is I'm doing what's called initializing the variable. The problem is that when the program runs, it's just going to grab whatever stored in memory when it gets allocated that RAM for that variable. It just grabs it, and so whatever's sitting in RAM from the previous program running is just what's going to get assigned to that variable. And so you can get any kind of craziness you can imagine assigned to it, and you do. So what you got to do is zero it out or clear it out to what you want to be a starting value for it before anything happens, so that you don't get that junk in there. It's always a good idea. It's standard good programming practice to do this. If you don't do it, what can happen is that you could go to add something in there and you're thinking, well, there's nothing in it, right? Nope, there's something in there, just don't know what it is. And then you'll be adding to whatever value was in there, and your results you'll get back will be completely crazy. And so you just won't know why that's happening. And that is the case with C, unless they've changed it in more recent years. Back when, it did not clear out the variables, and I suspect it still doesn't, so it probably never will. So you will need to initialize your variables when you first set them up here. Okay, so there we go with that. And then I need to find the voltage. I need to take inputs, two different things here. So one of the things I need to do is I need to say printf, and this comes from that library up here, this stdio. This is standard IO, it's short for standard input output. Alright, cool. And we need to basically print out, display to the screen. Print comes from an old term back when computers used to literally print on ticker tape or whatever it was, with vacuum tubes and everything on computers way back when. They programmed with punch cards and all this stuff. And so back when, it would literally be print, and people just never updated to change what stuff was called. So they still refer to print when you're going to display something on the screen. So that's where that's coming from. Alright, so anyways, we need to have the current. Enter the current. Something like that. Now, you don't have to do electronic physics formulas. I just am. Just thought this would be cool. I haven't done that in any of my videos, so I'm going to do some electronics formulas instead. So scanf, like so. Boom. Bada bing, like that. Alright. And what do I want to do? Well, scanf is going to let me have input. So it lets people essentially type in their input for their program, as far as that goes. Alright, so this is going to be a value that I need to let them input. And so it's going to be a floating point value, so I need to say %f here. If I said D, you're thinking, oh, that's going to be D for double, right? No, it's an integer. Integer, again, is a whole number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So watch out for that. That will catch you off guard on this. And then I'm going to say ampersand. Ampersand is a referencing the memory address of a variable in RAM. Again, I'm not going to get into that right now. That's too advanced for talking about entry level. Yeah. So we end up with one too many parentheses by mistake there. I just hit Control S there to save real quick. That's a hotkey for saving. Lets me save quite quickly. And there's my scanf. And so whatever they type in here for the current is going to get stored into I. And next I want to do the resistance. So I'm going to say um, print F. Now I'm lazy, so I could type all that out again, but what I want to show you is a cool trick. You come up here like this, hold down Shift, and use your arrow keys to select both those lines, and then you're going to say Control C. Control C lets you copy, and then if you do Control V to let you paste. And now I just copied and pasted that code, and it just saves me a lot of time because now I can say resistance. You could say it's futile, but no. R here. I guess resistance isn't futile, it's electrical. Alright, so here we are. And then now we can do a formula where we could say really that our voltage, right, is equal to R times I, or I times R, however you want to say it. Really doesn't matter. The terms can be flipped either way because multiplication order does not matter, right? Cool. And so what is that going to do? That is going to solve my formula for Ohm's law here. And we can have this equation here, like so. So what to do now? Well, we've got our result, and now we can say printf, and we can display the voltage, as it were. The voltage is alright. And I can say I need to do a floating point on this, so %f. Alright, something like that. And then I'm going to say a period at the end of this, so that way something of that nature. Cool. I'm going to say comma here, this point, and then I'm going to say, well, I think I'm just going to say good old, just the variable here. And I don't need to say anything else. I might do one more /n in order to keep things from being displayed on the same line. Yeah, okay, so I'm going to do that. Alright. So this V is going to get placed wherever the first thing is here, which is %f. Now I want to end this with a /n. I was trying to decide what to do for this. I'm going to start this one with a /n. What this is like hitting the enter key. So this takes it down to a new line character. So aka like hitting the enter key, moving it down to the next line. So that lets me separate it from this stuff here by one space. And then this lets me put space at the end so the prompt doesn't end up on the same line with my result here in my sentence. So I don't want that. So I'm going to put my /n at the end of this whole setup here. Just did Control S to save, or I could have come up here and clicked on the disk here. And afterwards, if I want to compile and run this, I simply hit the play button. And we have an output down here that shows the output. And it asks me enter the radius. Oh, this is a Java program. Alright, hold on. This is a whole nother program. Let me set find voltage as my main project right now. So set as main project. Okay, cool. Now, we won't be running a Java program anymore. Alright, enter the current. I don't know, 5. Resistance, 4. And so there we have. And then voltage is nothing. Why is voltage nothing? Well, that's bad. So our program worked for the most part, except for the issue of the fact that voltage is nothing at all. So a couple things could be going on there. Like the scanf may not be getting read in at all. And that would definitely be the issue on that. Okay, so basically what's wrong? Let's find it out. So if I do print here after what we did for input, printf here, and then we say %f like this with close comma I and comma r like that, and then a close parenthesis semicolon. It's going to display the two values that get entered in. So let's go ahead and run this and see what happens. So I run this, let's say 5 and then a 4, right? I should be getting 5 and 4, right? Instead I get 0, 0. So that's why our voltage is equal to 0, because when you take 0 times 0 equals 0. But you're going, wait a minute, we put in a 4 and a 5. Why aren't we getting that? Well, because I forgot it's not F, it's LF. So I think for long float, if I remember right. So, but when we go to display it back, it's just F. And I forgot about that. Just goes to illustrate how the slightest error can make something not work. So if I come in here and I say something like 5, 4, bam, it works. Now I get 5, 4, and my voltage is 20. So I don't need to display this anymore. Matter of fact, it's in the way, right, graphically anymore. So there we go, as far as that goes. And I'm just using that line to comment out that line of code there. So if I run this again now, it's just going to be 5, 4, and then we get 20, and we get what we want here. And we don't have to have that appear anymore. And so again, that's where that one line comment comes out. So it's a really great idea to, and we do this all the time, where we test basically our code by coming in here and doing a one-line comment out, or line of code, in order to reveal and hide it. And we use printf a lot of times to see what's stored inside our variables. Now, another way we could have done it is set up break statements. And what I could do is come down here and I could click on my square, create a square right here on line 27. And I don't want to hit play. If I hit play, it's not going to catch in debug mode. But if I come in here and say debug main project and run it like that, it's going to halt right there on that spot. And so it's going to run the other code above it first. So it's going to let me put in 5, it's going to let me put in 4, and then you're like, okay, so what's going wrong? Well, I can actually step in here, and I can step over things, stuff like that, and see what's happening inside this. And what's great about this is I can come in here, and I can come in and look at my variables. And then that's what's happening here. So I can look at it and see my V here, double is a 0, my I is a 5, and my R is a 4. And so we're literally looking at the values of these different variables sitting in RAM. So we're actually seeing the values in RAM. And you can get the program to do this. And you might be going, well, wow. In this case, argument C was just run with one argument. And then here we can see our argument list. And it has the whole argument list on what's getting passed into main. I'm not getting into that, but there it is. So yes, it does have values. This is what a memory address looks like. So 0xbffff774, etc. You get the idea. That is the memory address for that whole list of other objects here. And we see the memory address headed for this one here, and so on and so forth. So you can actually see what I'm talking about. And then you see 47 here with a slash being passed in on that one. I'm not getting into this, but you get to see that it's actually working on stuff getting passed in. Now, I don't do anything with this. If I wanted to, I could, but I'm not going to. But that argument list is there, and it is sitting in RAM. And our variables here for I and R are there with their values sitting in RAM. And, of course, it says there's one argument, and we just got to see one argument just now that was passed in to our argument list. So that's how all that works, and there's our voltage. Now, cool part about this, I can keep going here. I can step through my code. So what's wonderful about this is I can step into or I can step out of, run over. I can step over. I don't want to step into this, but I do want to step over it. So if I step over it, now check it out. When I stepped over it, check it out, V turned to 20. Why did it turn to 20? Because we said 5 times 4 is 20, and we said equal and assign it to the value in RAM for V, and it did. And so now you can see that V is 20. You can even come in here, and this is crazy, come in here and change the value in RAM as the program is running for testing purposes. So this is awesome. And then you can run it, and the result you're going to get from it will appear. So if I sit here and say, continue for play, the rest of it type thing, you can see the output of that. And the voltage was 18. You might go, no, it wasn't. It was 5 times 4. It's 20, right? Yeah, but I changed it in RAM before it got a chance to display that value. So if I run this again and just not mess with it, and just let it continue on the way it's supposed to, then it won't be an issue. Right? So again, we see these values here. I'm just going to step over it. Bam, it's now 20 here for V. I'm not going to change it this time. And I'm just going to display it out the rest of the way. And so it finished. Yay, happy day. We're done. And I hit play to finish that out. And if I come to my output, I can see it. Voltage is 20 because I didn't manipulate it this time. You know. So I could even come in here and say 20 volts. Yay. If I say play instead of debug, what now? You're gonna notice it's not gonna go into debug mode. It's not gonna break on that statement anymore. So that's the difference between hitting the play button here and the debug button. The debug button is gonna let me step through my code, whereas the play button is gonna let me step over the code and just basically avoid the whole process there. But anyways, there's that. If I want to get rid of my break statement, I simply just click on it again and it disappears, and we're good to go. Cool, cool. So there we are, and that's how that works. And that's how you can look at things in RAM and how things are running in the computer as they're running. It's really, really quite helpful while you're coding here to actually evaluate and see what's happening as you do it. And also it shows you some cool techniques for finding out an error and hunting it down. And actually glad I ran into that because it actually shows how you can use one-line statements like this, and then also going over how to use the debug tool to really help hunt down your errors and find your mistakes. It sure does make life a lot easier when you do that. So there we are. That covers that part. Now, what we could do, though, take this a little further and a little better than what we have already. And one of the things we could do is we could actually start to define these as functions and save ourselves trouble. It makes our coding easier. But to do this, I really need to define it kind of ahead of time here. So how do we do that? Well, to put it simply, we could create a pre-process function. It's not pre-process, but it's a prototype function. Basically, we're declaring the function is different than defining it. So if we come up here and declare it prior to our main, then we can put it anywhere we want in our source code, because then it'll know the existence of this function and we'll hunt it down and find it in RAM. I mean, well, yeah, in RAM when the program's running, but we'll hunt it down and find it in the code, put it that way. So if I created a function here, and I say like maybe double here for a return type, because we want to return double for our voltage, and you know, we might want to have a function called voltage. All right, we're going to find our voltage. Open close parentheses. Well, we're going to pass a couple of things in to this function. Really pretty much have to. So I want to pass in I, and I want this to be a double. And I need to do ampersand because I'm going to pass it by memory address. And I say double again, and I'm going to say ampersand because I'm going to pass it by its memory address. And I'm going to pass in the R for resistance too. So I got my NR and my, there we go. Now all has been forgiven by the computer, as it was very upset with me for not having the open and close curly braces. Because remember, these open and close curly braces are begin of a block of instructions, and a closing curly brace ends a block of instructions. So very, very helpful and saves you a lot of headaches trying to understand that. All right, cool. So one of the things I need to have, though, in here is I need to have a double here, and it needs to be R. So R is going to be, not R, I'm sorry, V. Gee, Christmas. V, like this. We already did that down below. I agree, we did. But what we're going to do is we can do it in here inside this function, and it makes it easier. And we can turn around and reuse this in the future if we want in our own header file, in our own .h that we can include. We could have all the electronics formulas, and then we can just include them and use them in our programs to solve different algorithms that need to be solved. So in R like that, PAM like that, And then I'm just going to say return. I like to put space between my return and whatever I had before. Then it's going to return v, semicolon, and it's going to return wherever the value of v was. Cool. If I wanted to, I could even get really short and simplified on this. Because technically, I'm wasting time and execution space by saying double v, declaring the v, and then returning it. So if I want to make this code shorter and sweeter, I can do that. And the way I do that is by coming in here and saying, boom, like this. And what I'll do is come in here and say return, and it's going to return the value that gets computed here. So I can compute this value and return the result, and that's it. So I can do this entire function in one line of code, as it were, with this setup here. So that's the other way to do it. So now it's going to return the voltage. And so instead of coming in here and doing it like this right here, instead I would come down here below and I would say V is equal to voltage. Close parentheses, and then I'm going to pass in. I have to pass it in the same order in which I did it. So I and then R. Alright, cool. Save. Like that. And I should get the same result. If everything went wonderfully, I should get the same result. And I'll explain this a little bit further here in just 1 second. And the bill failed. Of course it did. Why wouldn't it? So, project parentheses on line 16. Okay. So it's telling us we have an error. And the error we have is having to do with this definition part of this. It doesn't like it, matter of fact. If I look at the terminal, no, not the terminal, but the output. The output's telling us what the error is. It expected a semicolon or a comma or a closing parentheses before the ampersand. So this isn't a very good error message. Obviously, this is not the case of what I was trying to say. I could take away my ampersands if I like. Well, if my cursor is in the window, I can. Yeah. And so sometimes this will happen, where you'll get an error message, and you learn from experience that the error message is not accurate. And that was the case there. It didn't want the ampersands in front of these. From it, I think I needed it. So it didn't like that, and so because of that, it gave me an error message. Let's see something. Let me try it. Does it not like it that way too? No, it's not going to like it that way either. Okay, so it just doesn't want me to have ampersands on. That's weird. Maybe I'm thinking more of C++. I'm not sure. But anyways, it didn't want me to have those on there. It was going to have an error if I did. And you notice it didn't say anything about the ampersands. It was saying that it needed commas or closing semicolon or parentheses. And none of those were correct, what it was suggesting. Everything it was suggesting was incorrect. And it was really complaining about the ampersands. And I knew that the moment it said it, but what I was trying to do is pass by reference, by a pointer with it. So, I'm not sure off the top of my head right now why it didn't want the ampersands on there. Might not be remembering something correctly, because I'm used to passing stuff that way in another language. So, or maybe I'm just not thinking of something correctly. That's a possibility too. But what we're doing here right now, since we're not passing by reference, it really doesn't matter on this because they are just simple variables. It's not going to make a big speed difference. But essentially, we're just passing by value. And what this means is that it's copying this in memory. Let's see if I can't show you this real quick. Let's just pull this like so and put into debug mode. Alright. I'm just going to put in a 5 and a 4 like so. And it drops to this. If I click on this thing here, we'll see a couple of things. We'll see I and R. Well, it's not just I and R that's interesting. Notice that we've already read this other stuff in too. So, for instance, if we come over here, look at our I and R over here, it's a different story. So we can right click and add these to a watch. Let's see if it's in here or not. No, won't let me do that. Oh wait, new watch. Here we go. Let's say I. And I can also add another one called R. Now it's out of scope right now. For both of those. But basically what happened, I was kind of hoping I could show this, but I guess I can't, because it is out of scope, is that these are two different variables. Well, I guess you can see that. It's just this one's out of scope, so it's not showing it. But these are two different variables, and the values that were inside of I and R got passed to in I and in R. So they're totally two different variables. And that when this function finishes running, it's going to destroy the variables in RAM and the values that were stored in it. But we're going to return the result of voltage, so it's going to get assigned back to V before that happens. So that's what the return's all about. So what I'm going to do is I'm going to select this and add this to my watch here to create a new watch like that. Add V in there too. And then let's go ahead and step over this and see what happens. So we'll say step over here like that. And okay, so now it got returned. But these still exist in RAM. So see this? They still exist in RAM, but they're about to be destroyed. Boom. And you notice they're now toast. They're gone. They're destroyed. And they're not there anymore. But now V is 20, and we're back in scope on these. So now we can see our I and our R here. But it's not just that this is out of scope, it's toast. Once it goes out of scope here, these variables are created on the stack, and when a function or whatever, or when the variable goes out of scope, meaning scope would be these variables only exist inside of this function as parameters being passed in. So this is a parameter here, meaning a variable, and the value gets passed into it and gets stored into it. So we were copying what was an I, and we were storing it in the parameter variable of the function called in I. And then we were passing in the value from from R, and we were storing it in R here when it got typed in. And that happened when we did it right here. So when we said I here, it's going to get stored into NI like this. And just get stored in RAM. And I showed that earlier when this thing was debugging. If you need to, you can go back and rewind the video and watch again, see that being the case here when I was debugging. But I did that. And same thing here with R. So that R got assigned to NR like that in RAM. So took the value in RAM for I, and it stuck it into NI in RAM. And then this one, NR, got its value from R in RAM, and it passed that value to it and stored it in R. But these two variables only exist while this function is being run. So while this function is being computed right here, voltage is being computed, they exist. But the moment it's done running, after that, done with that return, they're all destroyed. They're destroyed from RAM because they only exist within the scope, aka within this function. Scope meaning within this function or some other block of code, but in this case, this function. And so this gets created on what's called the stack. The memory management on the stack is handled for us by C, by actual programming language itself, and we don't have to worry about it. But later on, eventually, maybe we get into stuff where we dynamically create RAM, create variables on the fly while the program is running and not at design time. This is design time where we're designing the code. Runtime means when the program is running. It is actually possible to create variables while the program is running. We're not going to do that right now. We're not going to do that for quite a while, matter of fact. That's more complicated by far. But essentially, once these variables went out of scope, they were deleted from memory automatically. If we were to create them in memory ourselves while the program is running, they don't disappear from memory. And we have to manage and handle that ourselves. And if we don't do it, we get what's called a memory leak. Or if we do it too soon and we try to access a variable that's already been deleted from memory, then we get an illegal memory operation and then the program crashes and dies. So it's more advanced. We're not going to do that right now. We'll worry about that later on. But for right now, we're going to just do this right here. Okay. And so there we go. We get to see that running. And I'm just going to say finish playing the program. And so now we can just see our output right here. And there we go. And that's 20 volts. And that's how we write a function. Alright, so I think that's enough for just the first intro video for C. And we'll look at getting into more advanced topics here in C in the next video. But for right now, I think this is enough for an introductory video on C. And we'll just move into some more advanced stuff in the next video. All right. Well, my name is Nate Nessler, and this has been for Hyperactive Studios. Thank you very much.